Okay, so for 2H, we are solving equations which involve modulus brackets. So not necessarily graphing these things, although you can do some graphing if you want to. We're just going to use algebra in order to solve these, pretty much. Okay, now graphing is going to be kind of useful to check our answers, and I might actually start with some of that as well. So let's have a look at these. This is example 16. So I'm switching the order of these ones. I just thought I'm going to say what I need to say from this one here. I think it's perhaps a little easier to start off with. So this one says solve the modulus of x plus 1, or the absolute value of this expression, x plus 1, is equal to minus 2x minus 5. And then it asks us to check our answers afterwards as well. Okay, so check your answers. Now, remember, of course, that the modulus of A is equal to two things. It's equal to A when A is greater than or equal to 0, and it's equal to minus A when A is less than 0. That's what we looked at last time. Okay, so in fact, this can be split into two things as well here. So we can say either x plus 1 is equal to minus 2x minus 5, and that's on the condition that this, like this, is greater than or equal to 0. Okay, so that's when x is greater than, or x plus 1, sorry, plus 1 is greater than or equal to 0, meaning to say, of course, that x is greater than or equal to minus 1. That there. And so that's one version, and the other version which we can solve is the minus of this. So we've got minus x plus 1 is equal to minus 2x minus 5, and that's when x is less than, let's put that again, x plus 1 is less than or equal to 0, or we can just say less than 0 because we've defined the full domain there. So if we take the 1 off, we're getting x is less than 1. So basically the opposite of this up here. Okay, so that's just coming from this definition for the modulus at the top. So basically, what are we doing? We're saying, well, this could be positive or this could be negative inside. Okay, we're not sure once we've taken the modulus brackets what we had inside. Maybe we had something which was positive, maybe we had something which is negative. Okay, so let's actually solve these ones then. So if we take the 2x to the other side on this one, we get it 3x is equal to, take the 1 across to minus 6, and that's equal to minus 2 there. And then if we just take both sides, so times both sides by minus 1, and we're getting 2x plus 5, and then take the x, of course, and take the 5 off, and we're getting x is equal to minus 4, which of course we'd normally write around the other way. Okay, so we've got two answers. So we've got this one and we've got this one. Now we just need to check that our conditions are correct as well. So that this solution does fall in the domain for which this part of the function is valid. Okay, so we've got the function being split into two here. We've got this condition for this. We've got this condition for this one. Okay, so x is equal to minus 2. This is telling us that x has to be greater than or equal to minus 1. So we can see that this is not true in this case. This does not fall in the category of greater than or equal to minus 1. So this cannot be a solution. There is a conflict between those two statements. Okay, and in this one it says x is minus 4, and we're being told that x is less than minus 1 here. So yes, that one is working. Now it does say check your answers. So you'd actually need to show that you're checking your answers by substituting this back in to the original function. So for example, you could say minus 2 plus 1 modulus of that equals, so that's our left-hand side, is equal to minus 1 modulus of that. And the right-hand side is equal to, and then check the right-hand side with minus 2 substituted. So minus 2, lots of minus 2. So we've got plus 4 minus 5. And so that's giving you there minus 1. So you see that the left-hand side is not equaling to the right-hand side there. Okay, so we can see that again there's this kind of conflict, and that does not check. But when we put this into here, you will find out that it does check. That's exactly the way in which the book deals with things as well. It says check with the left-hand side, essentially check with the right-hand side, and reject if the left-hand side doesn't equal to the right-hand side. Okay, so that's one way of doing it. Now I said as well that you can deal with this with graphs too. So actually, when I see a question like this, I'm kind of tempted to sketch the situation as well, to say, well, okay, what's happening if I say y is equal to this, and what's happening if I've got y is equal to this as well? I'm tempted to do that because I like working with graphs. So let's have a look. X plus 1, the modulus of x plus 1. So x plus 1 itself is this graph here. So it's going up in ones, and it goes through 1, and so it goes through minus 1 there. So the modulus of that is going to be like this. So that part's going to disappear. That's now the modulus of x plus 1. Could say that's y if we want to. And then the other expression, so this one here, is minus 2x minus 5. Okay, so minus 2x minus 5. So right now it's going to go through at minus 5, somewhere down here. And if we draw a gradient of minus 2 here, well, we can see that we're going to get, by going up 4, you're going to go across 2. Okay, so that's going to take us up here. So it's going to go, the next place is minus 3 comma minus 1. Okay, so all we're doing is going up 1, so up 2 and across 1. So, and then the next point, so that's minus 3 minus 1. No, it's not. Minus 1 comma minus 3. And then this point here is going through minus 2 comma minus 1. So I'm just sketching this thing out. And if I go through those, should we go through this one as well? I go through those and just draw that one up there. Then I can see that this, because this is steeper than this one, then at some stage up here, they're going to cross. But these two graphs are only going to cross once. Now it's possible that if I have another straight line, it could cross twice. Okay, or it's possible that they don't cross at all. So it's possible I get something like this and I get no solutions. So it's a bit like doing a straight line with a quadratic. Sometimes you get 2 solutions, sometimes you get 1 solution where it just touches, and sometimes you get no solution at all if you're trying to solve a linear function with a quadratic, and it's the same here. Okay, well, you didn't need to sketch the graphs there, but that's an example of as to how you could do that. Let's have a look at 15 now. So 15 is done slightly differently in the book, which is why I took 16 first. So 15, you have to do some manipulation to get this expression on its own to start off with. So let's take the 2 over to the other side. So we get minus 12, and let's divide by the minus 2 as well. Now we're left with this 3x plus 6 here. So we're saying that 3x plus 6, modulus of that, is equal to 6. Now, in the book, it then says, well, 3x plus 6 equals to plus or minus 6, saying, well, the thing inside here could have been plus or minus 6, get out the answer of 6. And of course, that does make sense, but that's slightly different to how we did the previous one. And so I'm going to stick with the way in which we did the previous one, which is to say this kind of general technique, say 3x plus 6, the positive of that is equal to 6, and the negative of this is equal to 6. So that's how I'm setting it up according to the definition for the modulus of A. So remember, it's equal to A or it's equal to minus A, dependent on A being greater than or equal to 0 or A being less than 0. Okay, so that's what I'm using in this case. I'm not saying is equal to plus or minus 6, but both methods are completely valid. Now, I should really put on here that 3x plus 6 is greater than or equal to 0, and 3x plus 6 is less than 0 there as well. So if we solve those ones, we're going to get x is greater than or equal to -2, and obviously this one needs to be x is less than -2. You can say less than or equal to -2. It's going to be the same at that point. Okay, so if we solve the first one, we get x is equal to 0. 0 is greater than or equal to -2, so that's good. And then if we solve the next one, we're going to get -3x is equal to -6. Take it to the other side, we get +12. So x is -4, and that fits in here as well. So that one works as well. Now that's not me checking them. If I have to check them, and it does say check them, you then need to substitute this back in to here and check that the left-hand side is the, sorry, not there. Substitute this back into the original function here and check the left-hand side is equal to -10, and then substitute this back in and check that the left-hand side is equal to -10 as well. Okay, let's do the graph version of this. Should we do the graph version? Yeah, let's do the graph version. So again, for the graph version, I wouldn't try and attempt to graph this. That's rather complicated. So it's obviously easier to take the 2 to the other side and then divide by the -2. So again, we're getting down to -12 divided by -2 is +6. And then we can graph this and see where it has a height of 6. So again, if we try and do this one, we're talking about 3x plus 6. So we know it needs to go through 6 on the axis, and it has a steepness of 3. So it's going to cross the x-axis at -2. So that's 2 across and 6 up is the gradient of 3. And obviously this one then needs to be changed to this. If we're going to take the modulus, so anything negative is going to become positive. It's going to go over to this side. So now this is our function of y equals the modulus of 3x plus 6. And now if we want this to equal to a height of 6, we can see that there's our height of 6. In fact, we could do this one completely geometrically, because we could say, well, x equaling to 0 is going to give us one solution as to where these two things cross, so for this place and this place. Given that that's at -2 and there's symmetry here, then this one must be at -4. So actually, you could do the whole thing geometrically for this question as well. Okay, well, let's look at next one. I think we've got one more. Here we go. They're talking about how to do it geometrically. That's kind of what I've discussed. So you can have a look at that. And example 17 looks pretty extended, but this is the last example here. Another quick exercise. These are turning out to be much quicker to do than to prep than the first chapter. First chapter is a lot more involved concepts, really. So example 17, 3x minus 4 is equal to 2x plus 3, both of those in modulus brackets, so absolute values of those two expressions. And check your answers both numerically and graphically in this case. Okay, right. So, well, I think I might just set up the graphs to start off with. So 3x minus 4. Okay, so I know this has got a steepness of 3. Okay, so I know that it's going to go through this point 1, minus 1 there. Okay, but that's at roughly a steepness of 3. And so the graph is going to look like this, and it's going to go through -4 there. So that's going to disappear. And then we have 2x plus 3, so the modulus of that. So this is going to go through +3. Okay, so that should be a +4 there. So it's going to go through +3, and then we're going to have a steepness of +2. So slightly less steep, this one. It's going to go something like this. Okay, it's going to cut through at -1.5 there. Okay, because that's going to give us a gradient of 2, and then we're going to have a less steep version going up like this. So this one should be less steep than this one here. This is a steepness of 2. When I say steepness, I'm just talking about the magnitude of the gradient there. Okay, so these two lines are never going to meet. And in fact, this line and this line will meet because this one is less steep than this one. So this is ultimately going to meet somewhere up here. So there is going to be a solution up there, and there's going to be a solution here as well. Okay, so there should be 2 solutions in this case, and one of them is just after x is equal to 0, and the other one is quite a bit further on. I don't know where it is, 10, something like that, somewhere up there. So that's me checking this graphically, and for you checking it graphically, you either need to plot it properly, because clearly this is only a sketch, or you can do it on your calculator, or you can do it using Desmos. So they're asking you just to check it using a graphical calculator. Okay, so let's get rid of this. I'm looking for 2 solutions here. And let's set them equal to each other then. Let's do that technique which we were talking about before. Let's say, well, we've got plus this thing, so essentially plus or minus this thing equals to plus or minus this thing over here. But hang on, that looks like we've got a lot of cases there. That's the plus of this, the plus of this, the plus of this, the minus of this, the minus of this, the plus of this, the minus of this, and the minus of this. But of course, there's just copies of the same thing there. If I take the negative of both sides, that's the same equation. I mean, I can get rid of that. And likewise, if I times one of the sides by 1, that's the same as me timesing the other side by 1. Okay, because I can times both sides by -1 here. So times this by -1, and I end up with this situation here. So in fact, there's only 2 things which we need to check in this case. So I only need to check plus plus and plus minus, either way round for plus minus. And that will sort everything out. So, okay, well, plus plus is 3x minus 4 is equal to 2x plus 3. Now, I'm struggling a little bit here to say what my domain is in each case, because my domain will be different in each case. So my domain here will be 3x minus 4 is greater than or equal to 0, and then 2x plus 3 is greater than or equal to 0 as well. So we've got 2 things which need to be satisfied in this case, and I'd say probably that's just getting a bit complicated to consider. So if 2 things have to be 2 things have to be satisfied, so let's say x is greater than 4 and x is greater than 3 have to be satisfied, then your x value you find has to be above 4, because both of those conditions have to be satisfied. I think, to be honest, that looking at the domains here is difficult and overly complicated, so let's just solve this and then check to see if it works. Okay, so take the 2x off both sides. X is equal to 7. Okay, super quick. We can check if that works by putting 7 back in here, and we're getting 21 minus 4 is equal to 17 on the left-hand side. And on the right-hand side, we're getting 2 times 7. 2 times 7 plus 3 is also 17. And 17, the modulus of that is still 17. So that one works. See, that's much quicker than actually thinking about your domains that work. Okay, so we've checked those ones. Okay, let's go back, and then doing now 3x minus 4. I'm going to make this one negative, and I'll make the other one positive. But of course, that's the same as making this one negative and this one positive. Okay, so we've got minus 3x plus 4 equals 2x plus 3. So let's take the 3x to this side, we've got 5x, and let's take the 3 to the other side, we've got 1. And we knew that it was the solution was just after x is equal to 0. We're getting out x is equal to a fifth, so we're pretty happy with that from the graph. Of course, you just need to substitute into the left-hand side and the right-hand side to check that you're getting the same thing from this as well. Let's just check. The book is saying Yeah, there you go. They're just checking both of those things as well. Check the left-hand side, check the right-hand side. And there we go. There's the graph version, which I was doing a sketch of, but that one's obviously much neater. Okay, so 2H, there's the questions. Make sure you get as much practice as possible. Next time round, we're dealing with inequalities with modulus brackets or absolute values. Okay, thanks for listening, guys, and see you next time. Okay, guys, back again here. I just forgot to mention a second method here. So for example 17, there was actually another method, and the book shows you this as well. And this is a method by squaring both sides. So when we've got a modulus sign on one side and a modulus sign on the other side, or if we've just got a modulus sign and an expression inside and just a normal expression, then what you can do is square both sides. Okay, reason why this works, I just stole this thing here, just copied this one up. And reason why this is working is basically because we've got, here we go, 3x minus 4, modulus of that equals modulus of this. But of course, that really means that we've got two functions for two different domains. We've got plus or minus this, depending on which domain is valid, okay, depending on how it's split up. And we've got equal to plus or minus this, again, depending on the domain of that one as well, depending on how that's split up, depending on where that bounces off the axis, essentially. One version is the plus version of the linear graph, and the other one is the negative. Okay, so we've got plus or minus and plus or minus, but when we square both sides, that plus or minus is going to disappear. So we'll just get plus 3x minus 4 all squared equal to plus this, because obviously when you square, you're only going to get positive answers. Right. Now at that stage, you can go ahead and you can solve these equations. So you can multiply this out, and you can see that's exactly what they've done here. You can bring everything to one side. Maybe you can factorize, or maybe you have to use the formula, or completing the square if you like. And you get your two answers. And then of course you still need to check the two answers, because this here is we still need to check that these two graphs cross at, say, for example, like this, cross at two different points, or maybe they cross at one point, or maybe they don't cross at all. So you need to check that those two solutions are in the valid domains for what we were doing before. We're saying, well, when is this plus and when is this negative? And that's going to be dependent on that point at the bottom. So you still need to check your answers in this method. And that's a really important last step. Okay, well, a lot of people like this method, so maybe you'd like to practice that one. But this method is limited because, I mean, how does it work if you say, I don't know, 2 plus square root of x plus 2 equals to 3? I don't know, we've got this, for example. And we square both sides there, but we're squaring an x plus or minus x plus 2 equals 3. When we square both sides, is it necessarily obvious that this is going to become positive? Complicated, okay? So I would only do this method here when we've got modulus on one side and either nothing on the other side or a modulus on the other side. So not when there's extra pluses and minuses on the end. I wouldn't do that. Okay, right, thanks for that. Thanks for hopefully getting to this point, and I'll see you for the next.